Welcome to The Explainer. Today, we're going to tune in to what astronomers thought was a perfect cosmic clock. It's a beacon in deep space, a timekeeper we set our own instruments by. But as we're about to find out, even the most reliable heartbeats in the universe can, well, skip a beat. So here's what we've got lined up. We'll start by getting to know this cosmic lighthouse. Then we'll check in with some citizen scientists in Colorado who are actually listening in. And finally, we're going to get to the heart of the mystery: why this supposedly perfect clock seems to have a split personality. All right, first things first. What exactly is this thing we're pointing our telescopes at?
Okay, so picture this. You've got the dead core of a massive star, right? It's been crushed by its own gravity until it's so dense, a single teaspoon of it would outweigh a mountain. Seriously. Now imagine that thing spinning hundreds of times every single second, and it's shooting out these powerful beams of radio waves from its poles. It's just like a lighthouse sweeping across space. And every time that beam zips past Earth, our telescopes pick up a pulse. And that, my friends, is a pulsar. So the star of our show today is PSR B0329+54. You can find it in the constellation Camelopardalis, and it is the brightest pulsar we can see from the northern hemisphere. It's so steady, so reliable, that astronomers actually use its signal to make sure their telescopes are working right. I mean, think about that. It's so important that it's one of the 14 pulsars used to draw a map back to Earth on those golden plaques aboard the Pioneer and Voyager spacecraft. It's not just a lighthouse, it's a landmark for humanity. And when I say reliable, I mean it. This thing does a full 360-degree spin every 0.7145 seconds. The precision is it's mind-boggling. It's truly one of the best timekeepers we've ever found in the entire universe. And yeah, this is no spring chicken. Scientists can actually measure the tiniest, almost unnoticeable slowdown in its spin, and based on that, they've figured out it's been pulsing away for over 5.5 million years. Incredible. So, how in the world do we listen to this ancient cosmic heartbeat from almost 5,500 light years away? Well, it turns out you don't actually have to be a professional astronomer with a PhD. This is where the Deep Space Exploration Society, or DSES, comes in. We're talking about a team of dedicated citizen scientists out in Haswell, Colorado, and they're using this huge 60-foot radio dish to listen to the cosmos. And here's a peek at their log from one of their observation sessions, where they were dialed right into our pulsar. And let me tell you, the quality of their work is just fantastic. I mean, you can see it right here in their own report. They called the signal outstanding, super strong and clean. It's just such a great reminder that passionate amateurs can make real contributions to science, capturing the kind of data where you can find some really cool cosmic secrets. Okay, so we've got this super reliable pulsar, right? And we've got great data on it. But this is where the story takes a turn. Because just when you think you've got this thing figured out, the data reveals a pretty deep mystery. And it all boils down to this. What if a perfect clock suddenly started changing its rhythm? Because that's what's happening. This benchmark, this gold standard for astronomers, doesn't always follow the script. It's got a secret. Yes, so researchers digging into the signal found out that it just spontaneously switches between two totally different states. Most of the time, it's doing its thing in what they call normal mode. But every so often, it just flips into this other, much rarer state they've called abnormal mode. So, get this. Over 41 hours of watching this thing, scientists found it spent about 13% of its time in this weird abnormal state. Now, for an object that's famous for being regular, that is a huge deal. It's kind of like finding out your trusty old grandfather clock suddenly decides to run 13% faster for a few hours every day. You notice, right? So what's the actual difference here? Well, it's all in the radio signal itself. The pulsar's signature totally changes when it flips. Let's take a look at this tale of two pulses. You see, the radio pulse we get from this thing isn't just a simple beep. It's actually a complex shape with a few different peaks. You can think of it like a unique fingerprint. But when the pulsar switches to abnormal mode, that fingerprint changes. One of the main peaks, which scientists call C3, literally shifts its timing and gets a whole lot brighter. And the numbers here really tell the story. In normal mode, that third peak is pretty weak, only about a third as strong as the main one. But in abnormal mode, whoa, it flares up, becoming more than 1.6 times stronger. And it even scoots a bit closer to the center. So this isn't some tiny little flicker. It's a major change in how the pulsar is broadcasting its signal.
But wait, there's more. The story doesn't actually end with the mode switching. This supposedly predictable star has another trick up its sleeve. There's another layer to this whole mystery. So, on top of those two modes, scientists spotted something else entirely. These super rare individual pulses that were just incredibly intense. We're talking more than 10 times the average brightness. Now, they're not quite the giant pulses you see from something like the famous crab pulsar, but they're definitely their own special kind of super bright signal. And what's really fascinating is that these bright flashes seem to depend on the frequency you're listening at. So if you're tuned in to a higher frequency, say a 3-centimeter wavelength, they're rare, but you'll catch them. But if you drop down to a lower frequency, like a 13-centimeter wavelength, they pretty much vanish. They're almost impossible to find. That tells us the physics causing these flashes is really specific and, well, kind of picky. Okay, so we've got this pulsar that's supposed to be as steady as they come, but it's switching modes and throwing out these random bright flashes. The big question is, so what? What does all this weirdness actually teach us? Well, the biggest lesson here is that these cosmic clocks are way more complicated than we ever gave them credit for. The fact that this mode switching happens at the same time across all frequencies means it's not just some random glitch. Nope. It's a huge, fundamental change happening in the pulsar's magnetosphere, that insanely powerful magnetic field that's generating the beams in the first place. It just goes to show you, even the things we think we know best in space can still throw us a major curveball and challenge everything we thought we knew about physics. And that really leaves us with one last kind of mind-blowing thought. If a pulsar that we literally use to calibrate our own instruments can be this complex and surprising, just imagine what other incredible secrets are still out there, hiding in the cosmic static, just waiting for us to listen in.